So today we will see MOSFET's DC characteristic. Last class we had seen the derivation of the current equation, right? Okay. So if you remember the current formula, you should see now. Drain current formula is given by ID is equals to mu n COX W by L into 2, and in bracket there is 2 times VGS minus VTH minus into VDS minus VDS square. And after that there is another term in a bracket which is 1 plus lambda VDS, where lambda is the channel length modulation parameter, and we will see how it affects. So what we said, we saw that the MOSFET device characteristic is such that the variation of the VDS, the channel length also varies, right? With the variation of VDS, the drain to source voltage, the channel length of the MOSFET also varies, and that causes an effect on the way the curve looks like. So today I am taking help of a software called LT-Spice. Many of you would have heard about it. So we'll take help of LT-Spice to see the DC characteristic, because I wanted you guys to see it rather than just take a theoretical note. I wanted you to see how they find the DC characteristic. Okay, so we will start with that. I'll share my screen. Okay. So you guys can see the screen, right? Okay. So now what you see is a LT-Spice. This is an LT-Spice software. Okay. And this is basically used to do a very variety of functions. So I'll come to the software later on. That is not a concern right now. Our concern is not to learn the software, but to learn what the characteristic is. So that directly I will go. Okay. So for now, ignore this. Okay. And this I will just okay. So you see, this is a basic MOSFET. This is a NMOS. Okay, and I have applied these voltage sources. Using these voltage sources, I am applying a gate to source voltage so that I am biasing the MOSFET, right? So we have the VGS, we have the VDS. I have kept the name as it is, just like we write in the formula. That is how I have kept the name. Okay. So you all know the formula, so keep that formula in front of you. Okay. So we will see how we get the DC characteristics. Okay. So what is V2 here? V2 is nothing but VGS, right? And V1 is nothing but VDS. Okay. So keep that in mind. So now you see I am just running a DC operation. Since we have to see DC characteristic, I am running a DC operation. Okay. And I am varying V2. Here you see my pointer, you can see, right? This plus, a slight plus is coming. So here a DC operation is there, okay, which is varying V2 from 0 to 12.2 volts, okay, and by a fact with a tick of 0.1. So let me just show this to you. Yes. So see, I have taken first source as my V2, which is nothing but VGS. So I am varying VGS, okay, linearly. Start value is 0, end value is 1.2, and I am incrementing by a factor of 0.1 volts. Okay, and the second source sweep is V1, which is nothing but VDS, and similarly I am varying VDS also. Okay, so why I am doing this? Because you remember in the transfer characteristic, if you remember what we used to do, we used to see, so what is basically a transistor? That you are varying the voltage at one point and the current at another point is varying, right? So basically we vary the voltage at gate and we get a drain to source current which is varying because of that. So we will try to check that here. Okay, so I'm just running it. I'm not explaining how the software is. So I'm simply running it. Okay, now the x-axis that you see here, it is VGS. Okay, it is V1 because so I can show you. So I write it is V2. V2 is VGS. Okay, so if you see here, this one VGS was V2. Okay, so x-axis is here VGS, and what I will do, I will now plot. I will plot what? I will plot the drain current of M1. So if you can see, ID bracket M1 is written. M1 is the MOSFET. Okay. So if I do OK, you see this is how the input characteristic looks like. Is it clear? Right. Now it is showing for different values are there, right? Different colors are here. So let us see what are those colors. See legend. So basically it has run for different values of V1. Okay, I hope you can see. So V1 was nothing but VDS. So what is happening? I have taken a MOSFET. Okay, I have taken a MOSFET and I applied a source voltage to it. Applied a DC, a varying DC. And I also applied a varying DC to drain terminal of the MOSFET. Okay, and now I am varying them both. And I am monitoring the drain current and I am plotting it. I am keeping x-axis as VGS and y-axis as that current ID, and I am also varying VDS. So now what is happening? When my VDS is 0 volt, that is I have not applied any voltage, you see the green line is a straight line, there is no current, right? So now as my VDS is increasing, you can see that there is an increase in value of current also, right? How will you understand it? How do you understand? So you see at any point at 0.9 volts VGS, you see there is an increase in the current ID with increase in VDS, which is what we should see, right? With the increase in VDS, the current should increase and then get saturated at some point. So what is input characteristic mainly used for? It is mainly used for understanding where my threshold voltage lies. So you see a point here, you see my pointer, you see a point here. After this point only, the current starts flowing, right? So around this point, you see my pointer, around this point, the current starts increasing. So the V threshold of this MOSFET will be anywhere near your this thing, where anywhere near your 0.5 volts. Okay, so V threshold will be anywhere near your 0.5 volts. Okay, so is this clear here till here? Any questions here? So this is the input characteristic. So you can draw it also. Okay, so please draw it in your copy. You take x-axis as VGS, y-axis is ID, and this is for incremental values of VDS. Okay. Okay now. So now next what I will do? I have to see VDS as x-axis and ID as y-axis. So I'll just change it again. So now I want to take VDS here I think I have to run it again. Okay, let me run it again. Close. So now I'm just changing the axis. Okay, and I'll run it. And again I will plot the trace. You can see the output characteristic now, right? Familiar with the output characteristic? The current increases with VDS. As VDS is increasing, ID is also increasing, and after a point, after where saturation is reached, so you see it is somewhere here, somewhere here the saturation is reaching, right? VGS minus VTH. Somewhere here the saturation is reaching, and after that the current is constant. But if you see carefully, it is not a very straight line. It will never be a very straight line. Instead, it will be a bit tapered, and we will see that. So here also I'll plot the legends, add traces. Sorry, not traces. I'll add the legend, view, step legend. Yeah. So now you see for different value of VGS. So when VGS is 0, VGS is 0. Okay. What is the trace coming? This one, the first one, right? Then the first one here, from here. Okay, so the VGS is 0, current is 0, and when VGS is the highest, this is the first one, so this is the highest one. So VGS is increasing from bottom to top. Okay, so this is the highest value of VGS, lower than this, lower than this, lower than this, lower than this, like that. Okay. Okay, because MOSFET is a normally off device, right? Enhancement MOSFET we are seeing. So as we give the positive voltage in one NMOS, the voltage will keep on the current will keep on increasing, because then the inversion layer will form. If you remember, we had studied that as we keep on reverse biasing the gate, then the inversion layer keeps on increasing. There is an inversion layer present, and that inversion layer will make sure that there is a channel formed there, right? So as we keep on increasing the value of VGS, then the inversion layer will have more charges, and therefore the current will increase. But since we are also increasing VDS here, the increment of VDS, what it will do, it will pinch off the channel. And once it pinches off the channel, the current can no longer increase, but the current is not 0. What will happen? Because of the built-in electric field, the charges with a constant velocity, they will just surpass the pinched off region and reach the drain. So okay, so from source to drain there is a flow of charges, and that leads to the current. And here you can see that the gate to source voltage is also controlling that. So this is what is a transistor action, right? So we are controlling VGS, and according to that we are getting ID, right? We are getting ID. So is this clear? I hope this is more interesting to visualize. So VGS, you can see it is increasing from bottom to top. Top is the highest value. For PMOS, it will just be opposite. It is just a matter of like opposite polarity. It is nothing else in PMOS. Okay. Till here, any doubt? Okay. So one more thing that I wanted to show you. Okay, here's one interesting thing also. You can see that we saw that the VTH, that is the threshold voltage, that was near about 0.5 volts. So let's verify that. Okay, so for that there is an operation which actually finds out the DC operating point. So we'll just run that. Okay, so I'll run that. And you see this is a DC operating point. So when VDS is 1.2, VGS is 1.2, it is showing me what is the condition of the MOSFET, like what are the currents that are flowing. Here you see there is a voltage from drain to body also, it is showing. right? This is substrate to body, source to body, and drain to body, right? So this is also it is showing. So here you can see, yes. So this is what shows, see, VTH is 0.423 volts, right? We saw it was near somewhere 5 volts, the 0.5 volts we saw, right? So here you can see it is coming near about, VTH is near about 0.423 volts, okay, for this NMOS. And the GM, you can see GM value is also there, and these also are always in SI units, okay, so that is in volts, okay. GM also is given in mho, okay, that is in mho, ampere per volts, and likewise you can find other values as such here, okay. And the condition is also given. So VTH obviously it will not change, so this is the condition at which GM is this. As the condition varies, our values will vary, but here you can see and you can have a cross checking here, right? So I hope this was interesting enough. So if you want to learn this software, I have short tutorial videos, the links of which are in my website. I'll try to put it on YouTube as well. I have not put that on YouTube actually. So, but in my web page, you will find that I have these links as to how to start with LT Spice, and this thing you will not get in other YouTube videos. This is a different thing actually. In Normally in YouTube videos, if you want to learn LT Spice, they will be using like already IC components they use, okay. But here these are not IC components, these are normal components, and I have used some technology node files for some different spice files for this. So that is a completely different approach to LT Spice that is there in those videos. If you are interested, you can go and see, but there is no compulsion. So I hope this was interesting enough. So this 25 minutes, whatever we have discussed, and it is a part of your GATE syllabus that can come. Okay, we will see the questions. When we see, we will understand. So we will solve some questions now related to that. So before that, I just want you to pause and uh, like think whatever we have done. Okay, any questions here? Okay, so then I will just stop sharing. Okay, so now as we saw that in the MOSFET, this is the drain terminal, this is the source terminal, this is the gate terminal. Remember, gate, drain, source. So drain and source are decided depending on the potential that is applied, okay. So drain VD will always be at higher potential than source, okay. Then only I can say that is source. It is not decided by the arrow, not. So you have to be careful if VD is always greater than VS. But normally when we write the symbol and we are not applying any voltage, we are just showing it. This is how we take the arrow to be source, okay. And we saw that how its characteristic was coming up like this, right? Okay, so okay, one more thing I wanted to show you which I missed. So let us do one question and then after that I will show you. Maybe at last I will show you again. So anyways, so the question that we are going to see now is, so these kind of questions can come, okay, but I don't know how they will ask it. The method of asking may be different, but how to analyze the question is what I am going to show you now. Please draw the figure that I am drawing right now. So this is all DC analysis question. There is no AC analysis involved. So we are just going to do a DC analysis of the MOSFET, okay? Please note down and let me know once you have noted it down. And these questions, please make a careful note of it, okay? And you can refer it while doing your gate preparation. And I don't think normally, like in my time, people did not deal with these kind of questions, but I now see a necessity of dealing with this. Please let me know once you have finished writing. Okay? Okay. So now, what do you understand from this question? First, there is a V out from this node. So once we see it, what we think, okay, the source is getting a 1 volt. So we quickly write Vs is 1 volt and Vd is V out. Okay. And V in I know from 0 to 3 volt. And the moment you have done this, it is wrong. This approach is wrong. Wrong approach. Why? So just now I told you that the source and drain terminal is decided by the potential that is applied. So here in the MOSFET, you can see that there is a potential applied. There is already a voltage source, a fixed voltage source, right? Fixed source, fixed DC source at this node. And V out is nothing right now. V out is just, I am taking V out from this terminal. I am not applying. This is the output, right? Okay. So now V in is what is again a DC source, which is varying 0 to 3 volts. So now I know that when V in is 0, that means the MOSFET is off, right? The MOSFET is off. Say, considering this is source, then VGS is what? Considering this is source, VGS will be something negative, right? And even if I consider this source, then also there is nothing, there is no V out. So MOSFET is off. Is this point clear? Initially MOSFET is off. So why is it off? Is it clear? Or should I repeat? So first point you should write in your notebook, MOSFET is off when V in is equals to 0 volt. This you should write. MOSFET off when V in 0 volts. That is your first point. Okay. Now, since MOSFET is off, V in is 0 volt, V out is 0 volt because there is 0 current flowing. So no current from R1, 0 ampere from R1. So V out is 0 volts, right? So now if V out is 0 volts and Vs is 1 volt, so this point is, this node is 1 volts, then what has happened? The drain and source has now interchanged, right? The arrow is not the drain because as we said that it will depend on the potential. So the MOSFET can be now redrawn as now this seems easy enough. This if you see you will say okay, I know this structure. But the earlier structure that was given, earlier structure was and if you see this is the same structure. It is the same structure. Why? Because we cannot decide source and drain with the arrow. Arrow does not decide source and drain. Okay, so source and drain, how will your source and drain be decided? So if you remember, so Chandrasekhar is asking why. So last class we saw this diagram, right? And what is happening here? The drain is getting a potential here, right? Plus minus. And the source is grounded. So drain is getting a positive potential, more positive than source, and that's why the current was like this, right? You remember? So now if I had put it just the opposite way, if I had connected it plus minus here and have grounded this, right? These are basically symmetric terminals. In BJT what happens? Emitter, right, because of symmetry, in BJT is an asymmetric device. The emitter, collector, base are differently doped, but in MOSFET it is a symmetric device. It is equally doped. So depending on where I put the potential, now the current will be in this direction. Because now this has become drain, this has become source. Okay, this all comes from MOSFET's construction. Is it clear to everyone? It is a very important question, and it's important to understand it because from gate point of view, if I say, in gate they ask questions like this only, so that it's tricky for you. Okay, they try to make it tricky for you. And even after gate, it has been seen that if you go for this interviews in IITs, okay, they take the, I think IIT Madras now take interviews. I don't know about other IITs. Initially everybody used to take interviews for MTech admission. So it is a very hot question, that which one is source, which one is drain, they will ask you, and you cannot say that this is source and this is drain. You have to say that it will depend on the potential where I apply. Okay, so now is it clear why this structure is like this? So this is a very easy structure, right? The left hand one is something you have always seen, but the right side one you have not seen, right? You have not seen this. Okay, so now we will continue with the question. Okay, so we will now solve which diagram? We will solve this diagram. So I can basically solve this one also. I'll do the same thing, but for ease I have drawn it like this. Okay, okay. So now what will happen? This is VGS, right? Plus minus VGS. Huh? And VS is nothing but V out. So that means VGS is nothing but V in minus V out. Any doubts here? Basic KVL. VGS is V in minus V out. And what is VDS? VDS is 1 minus V out. Is it fine? Okay. So now if I say that, okay, give me the condition. So VDS should be greater than equal to VGS minus VTH for saturation. That means 1 minus V out right. I'm taking the equal to condition. I'm not taking the non-equality. I'm taking the equality. Okay. And we had seen earlier in the question, VTH is 0.7 volts. This implies Vn is, so greater than Vn. After Vn has reached 1.7 volts, my MOSFET will reach saturation. This MOSFET will reach saturation, right? And what will happen after that? Can V out increase from 1 volt? What will happen if V out starts increasing from 1 volt? Then what will happen? This will become drain, this will become source, right? And you will see it from analysis that this cannot happen. V in, V out has to, the maximum value of V out that will reach is 1 volt. The maximum value of V out that it will reach will be 1 volt. Okay. And why is that happening? You can take values. You can take V out a bit higher. Okay. You can take a V out value that is higher for a higher V in. Okay. And you will again and again, you will see that you will arrive at a point where it cannot go, you will arrive by intuition, you will arrive at a point where it cannot go more than 1 volts. Okay. So what is happening is, suppose Vn is in this. Okay. So now I am writing it here. See, V in is 0 volt, V out is 0 volts. Fine. Now V in started increasing. V in became 0.7 volts. Okay. V in became 0.7 volts. After V in became 0.7 volts, MOSFET was on. Okay. And V out started increasing. V out is increasing. Slowly it is increasing. Now V in reached 1.7 volts. What will happen? V out will reach what value? We had seen it. When V in is 1.7, V out will reach 1 volt. Now when V in is 1.8 volts, VGS we know what was the VTH? It is 0.7. So I cannot say that V out is 1.1 because now again drain and source will invert the functions, right? And once drain and source has inverted the functions, you will see that you will reach at a point where V out is still 1 volt. It cannot go beyond that. Okay. So I think it was not coming because of internet. So V in is 0 volt, V out is 0 volt because no current is flowing. V in 0.7 volt, MOSFET turns on, V out starts slowly increasing. So let me draw. So if this is V in, this is V out. V in is 0.7. So V out slowly starts increasing after 0.7 because current had started increasing. And once V in is 1.7, V out reaches a point where it is 1 volts. And after that, after V in is increased, V out cannot increase beyond after that point. If V out increases after that point, the drain and source interchanges and again V out is at 1 volt. So you see V out is saturated at 1 volt. Okay. So analyze this question after the class. Please analyze it. You can write this up. This thing you can write. So just quickly rub this part so that it is clear for you. And let me write this here. Okay. So write this thing, you write first and after that you write the black portion. Okay. So once you have written it down, let me know. We'll do another question. In that also it will get clear what is happening. So V in is basically varying from 0 to 3 volts. Okay. So till 3 volts, from 1.7 to 3, V out is 1 volt. Please let me know once you have written down this question. So in these kind of questions, you have to basically see two things. First is when the MOSFET is turning on, and second is when it is reaching the saturation. So the saturation point will be VDS equals to VGS minus VTH. That is the condition that will tell you the output voltage. And then you have to see that after that point what is happening. Whether it is getting saturated at that point, or it is again it can vary or not. Those things you have to check. Okay, so we'll do another question. It will again become clear then. That question is also similar to this one only. Okay. So in the earlier question, the varying Vin was at G. Now the varying Vin is at this point, right? And it is just like the earlier question that we will see that V out is 0 volts at first. There is no current flowing, right? So what I can write? I can write this as so this is the question. So basically nothing, but you have put a fixed voltage Vg 2 volts and you are varying VDS. And you have seen that we have done this earlier also, and this is just like the output characteristics like this, right? Because this is varying, Vin is varying from 0 to 3 volts, right? And then at after some point it will get saturated at some value. The V out will get saturated at some value. We don't know what value this is. So this will be found from the equations. This entire equation that we have studied, these equations will be used to find out these values of steady state values. Okay, but I don't think in GATE they will be asking you that much complicated. Mainly they can ask you graphs and all. Even if they ask you, it will depend on the simple saturation formula only, because after this point it gets saturated, you just put in the values and you get the answer. Okay, so here you will see VGS value is nothing but 2 minus V out, right? And VDS is V in minus V out. So if you use the saturation region condition, it will be V in minus V out equals to 2 minus V out minus VTH, which is 0.7, and from here you will see V in is coming as 1.3 volts. That means after V in 1.3 volts, the current will get constant and so will V out. So this is 1.3. Okay. Is this question clear? Please let me know once you have written it down. And even if you are not able to understand everything in the class right now, just analyze it after the class. Okay, these are all analytical questions. You have to sit with your pen and paper and you have to analyze it. Okay, and then you can ask me the doubts in the next class. Whatever doubts you have. And these are Razavi's chapter 2 back answer questions. Okay. These are all unsolved questions only. So these are there are a lot of questions like this. I won't say that you solve everything, but you can have a look at it. The questions are good. Okay. Okay. Let's go to next question. So these MOSFETs can be very well asked with caps. Okay. So They can ask you a question like this. Right? So these are capacitors C1, C2. So C1 and C2 initial voltages are given. They are already charged. So C1 and C2 are charged to 3 volts and 1 volts respectively. Okay. Vg is given as 2 volts. So now you can see that Vx is 4 volts, right? And this node here is 3 volts. So that means your drain is 4 volts is Vx and Vs is 3 volts, which matches because the potential is higher at drain. Is this fine? Okay. So now what will be Vx? So if the question can be what is the steady state value of Vx or the final value of Vx, like that they can ask, right? So what is happening with ds, if you see, what is it? 4 minus 3, 1 volt, right? 4 minus 3, 1 volt, and Vg is 2 volt and Vs is 3 volt. That means MOSFET is off. So if MOSFET is off, there is no current. That means whatever charge the capacitor is having, it will hold that charge. And therefore Vx will be 4 volts only. That is the answer. This is a very simple 1 mark question, can become, right? It's very simple. So basically if you see the graph, Vx is constant at 4 volts in ideal condition, taking ideal caps, and Id, if you see, it will always be 0 with respect to Vin or something, whatever, sorry, with respect to time. Okay, so this can be a very simple 1 mark question, numerical answer type, because it's pretty simple, right? So please take a note of this. So like this, there are more questions in Razagi's book, which are good. And I think if they want to make a interesting paper, they can put this kind of questions on paper. Okay. So till here, if it is clear, then yeah, I can take one more question with these caps. Okay. I'll take one more question and then we will go to LTSpice again and I'll show you one more thing and then we will end the class. So have you noted this? So Chandrasekhar had asked that how V out is 1 volt. So earlier in that question, Chandrasekhar, I think just go through that solution once, try analyze it, and then in next class we will discuss. Okay, I'm sure you will able to understand why it is getting constant at 1 volt. Okay, okay. Same for everybody. If you have not understood, try analyzing it. We will discuss it in next class. Okay, if you want to see the previous question, this is done. Yeah. This was the second question that we did. And this is the third question. Okay, so let's move to the fourth question. Again, a simple question I'll take. So we are giving a step voltage which is varying from 0 to 3 volts. So at t equals to 0, it has become 3 volts. Okay, and the capacitor is already discharged. The capacitor is already charged with 1 volt. Okay, so now intuitively you see what will happen. Intuitively, if you see that I have given a favorable condition for VGS, VGS will be 3 volt. After the step has reached 3 volts at input, VGS is 3 volts. Okay, so that means the MOSFET will turn on. So if the MOSFET will turn on, then the cap will get a path to discharge. There will be a current from this path, right? ID. So that will be acting as the discharge path for the cap, and the cap will finally discharge to 0 volts. So Vx finally will be 0 volts. This is what should happen. Now we will verify whether it is actually happening or not. Okay, so if directly some numerical answer type is asked, then you know the answer. If some graph is there, then you might have to just do some calculation, or you might not have to do calculations also. Okay, so we'll see why. So I'm writing ID. So I'm starting the current with the equation where MOSFET is actually in triode region. I'm assuming it is right now in triode. Okay, so why it is in triode? Can anyone tell why the MOSFET is in triode region? Assumption is correct. Anybody? Just look at it, the figure. What is VDS? VDS is 1 volt. And what is VGS? 3 volts. So VDS will be less than VGS minus VTH, right? That's why MOSFET is in triode. And it will always be in triode because Vx will be going towards 0 volt because capacitor will discharge, right? So had this voltage will be more than 1 volt, 3 volts, suppose this voltage was more than 3 volts, then there was a chance that we can say that okay, it is in saturation, and we will use saturation's formula, or otherwise we will use triode's formula, which is ID is equals to, I'm just writing Kn dash, okay, Kn dash by 2, which is 2 times VGS minus VTH, so 3 minus 0.7, VTH is 0.7 volts, into VDS 1, okay, minus VDS square 1 square, okay, this is what it should be, right? But now what we are saying, we are going to find the equation of Vx, so we will write Vx and Vx square. We are not going to use the 1 volt, okay, because we are trying to find the complete charge profile. It is 1 volt at t equals to 0 plus, so we are using the triode's formula, and we know that it will be in triode region after that. But when if I want to find the entire graph, I have to use the variable, and this will be equal to what? This will be equal to what? This will be equal to minus C dVx by dt. Is this clear? Because this is capacitor, right? And I'm taking the current across the capacitor. The direction of ID is this, and the positive direction. So the capacitor current, the ID will be in this direction from the capacitor, and therefore there is a negative sign. Because actually from the sign of the voltage, it should be this side, right? So this is minus C dVx by dt. Is this clear? By the negative sign? Okay. So after this, if you solve this, okay, I'm not doing the entire solution here. You can take all the constants to be some alpha, and it will come out to be like this. So this Kn dash by 2 into C, everything I have taken to be alpha, okay. It doesn't matter because anyways we are going to find the graph, okay. So therefore minus alpha dt equals to dVx upon Vx into 4.6 minus Vx, right? And this you can separate out, right? This is nothing but a what? Exponential form. So in GATE mathematics also you are having this, right? That this differential equations you have to solve and all. So this is there you will study it. So Vx you can find, it will come, I think it will come around this, something like this it will come. So it doesn't matter what exact values it is coming. What matters is what kind of profile it will carry. Okay, so what it is some negative exponential. So it is something of the form e to the power minus x, right? Because it is like something 1 by 1 plus e to the power x, suppose. Okay, so I'm just writing it. So this is basically nothing but in the form of like this, right? Inverse, so negative form. So what will happen if you put a 0 in place of t? You get 1 volts, you see. So Vx at 0 is 1 volt and Vx at infinity is 0 volts. Somewhere at infinity it will reach 0. Okay, this is Vx with respect to t. Is this clear? You can note it down. So this was our last question for today. Please note this down. So this kind of questions, if they want to make the paper a bit more tough, this kind of questions can come. They can use the capacitors and you have to do a transient analysis here with the capacitor and MOSFETs. Okay. So I hope now these things will be beneficial to you, but because as far as I know, these topics are not dealt with everybody. If they in YouTube channels and all, normally they don't deal with these kind of topics. So if you can get an idea about it, it will be good. Okay. So let me know once you are done, then we'll quickly shift to LT Spice once more. I just wanted to show you one thing. MOSFET questions, Chandrasekhar. First, you finish the previous year GATE questions, okay? And last IIT Madras paper you just see. I think IIT Madras framed it in 2019, I think. So 2019 Madras paper, you will see 2-3 questions are very good questions of MOSFETs are there. You try to go through that, okay? And once you have finished the GATE questions, then from this Razavi's book, you can solve some back exercise problems you guys can solve. Not everything. Some problems you can solve. Yeah, just for MOSFET I'm saying. So see the normal formula based questions are very easy. That you need not practice from anywhere. But the questions like this capacitor problem. So these kind of questions you will need to do a bit of practice. It can be asked in exams. Okay. There is a chance of this type of questions coming. And keep your concepts of network transient analysis very clear. Okay, so if you know MOSFET how it behaves, and if you know a transient analysis of capacitors and inductors, you can solve the question. Even if you have not practiced that much, you can solve the question. That is my belief. If you separately also, if your concepts are clear, you can merge it together and you can solve it. Okay, so should I move to the next part? Is this done? Because I have to stop sharing the screen then. Okay, others are also done. So Chandrasekhar has put a yes. Others are also done. Okay, so let me just stop sharing. Okay, you can see the window again, right? LD Spice window. Okay. So here what I'm doing is, uh, here also I'm wearing, so here everything else is fixed. I'm wearing VDS, okay, and I'm also wearing the channel length of the MOSFET. So how to do that? Here you can see that in the MOSFET I have just put a variable in place of length, and I have declared a width of the MOSFET. So MOSFET current equation is having a aspect ratio, right? W by L. So unless you specify a aspect ratio for your MOSFET, it will not work. So W and L value you have to specify. Okay. So here I have put a variable L. So this is a 60 nanometer device. Okay. So there are different technology nodes. So when we fabricate the MOSFET, it is in nanometer scale VLSI design. So during the fabrication, there are different nodes. So 180 nanometer, 130 nanometer. So this is a 65 nanometer node. And how it is a 65 nanometer node? This include file you are seeing here, C program files. So I have basically included a spice file which will make sure that the MOSFET I have taken is a 65 nanometer MOSFET. So these things, if you want to learn, you can go to the web page and learn it. If you don't want to learn, that's fine, completely on you. Okay. So just wanted to show you that when, as I wanted to show you the channel length modulation basically. So 1 plus lambda VDS, right? And lambda is inversely proportional to length. So that means if length increases, lambda will decrease, and 1 plus lambda VDS will decrease. And my current will be more towards the constant current, which is the actual value, because 1 plus lambda VDS is now small, right? So we'll just run it, and we will add the trace ID drain current, and now what you see is not because of VGS. These three values are not because of VGS, but because of the length. You see, length is 60 nanometer, length 60 nanometer, green color. See how the curve is going, right? It is just passing like a such a high slope, right? Then when I did 180 nanometer, you see it has come down, it has become constant, and then you see at 300 nanometer it is further constant, although the current value has also decreased, because id is inversely proportional to L, right? Id is equals to mu n Cux W by L. So id is also inversely proportional to L. So id will also decrease, but it will be constant. So whenever MOSFET is used as a constant current source, the L is always kept high. So this can also be a objective type statement question. It can be a statement question that for a current source MOSFET, they can ask like for a current source MOSFET's channel length is should be kept high, like that they can ask. Or they can ask, as channel length increases, what happens? R out increases, right? Because R out, if you remember, right? So that's how they can ask you the question. Okay, so for constant current source, you can see that the channel length has to be high. Okay, so this is what I wanted to show you uh, practically. So remember, this is not because of VGS, this is because of this varying channel length. So is this clear? So I hope with this visualization, you will now easily remember MOSFET's characteristics and behavior. Okay, then it is past 5 o'clock now. So I think we'll end the class here. Okay, and in the next class, we will start with the small signal analysis. We'll finally start with small signal analysis, and then we will do some questions also. After small signal analysis, we will do some questions. Okay, in the next class. Okay then. Okay. If any doubts, you guys can mail me, and yeah, and I have uploaded the previous videos in YouTube, and this video also I'll do. Okay. Okay then. Have a nice day. Bye.